Section 9.3 is all about logarithmic functions. The topics are not listed here, but they are at the beginning of the book. Log base A of x. The most important thing to remember about log is that log is a function. When you take the log of something, it's a function of something. So for example, this is the log function of x. In this case, my base is a, log of x with a base of a, or log base a of x. So when I think of log, I think about a tree. So that doesn't make any sense to me mathematically. So the most important thing for me is when I see log, I automatically am going to turn it into an exponential equation or an exponential function, because log is exactly the same as an exponential function, because as we learned in 9.2, log is the inverse of exponentials. So if we look back at 9.2, we left off here, where we saw that log, right here, this is the log function, is the inverse of the exponential. Well, log is an exponential function, but it's the inverse one when y is the exponent. Okay, so that's really important to understand. Even though log and exponentials are inverses, log is an exponential function, but it's the inverse of the exponential function, which means log will have x equals to the exponent of y. So now my x is no longer my exponent, y is my exponent. So that's the inverse of the exponential function, and that is also exactly equal to log. They are equivalent. So back to 9.3, when I'm looking at log, first thing I notice is x is greater than 0, a is a positive constant other than 1. Just like our exponential function, my a value, which was the base, had to be positive and it couldn't be 1. Essentially with this next sentence, it doesn't really make sense to me, so let's look at what it really means. Log base a of x equals m. So if I have log of x with a base of a equaling m, it is exactly equal to a to the m equals x. What that means is I can change any logarithmic equation, expression, whatever, into an exponential expression, which is what we understand. Log doesn't make sense to me. When I see log, I'm like, okay, a tree. So I'm going to change it into an exponential because I do understand that. So that's very important to understand that a log is exactly the same as an exponential. My little thing that I made up is called under to the over equals. That's how I remember how to change my log correctly into this form. Under, you take the base, under, so the base of log is going to be the base of your exponential. So under to the over. To the means that's my exponent, to the exponent of, to the m equals, cross the equal sign and you will have an equal sign x. So if I ever see a log, I'm going to automatically put it into this form because I understand exponents. I do not understand log. It's a function, it's a weird thing, it's hard, okay? So equivalently, what this expression says right here, a to the log base a of x equals x. Because your log is base a, if you raise that from another base of a, those will cancel each other out and you will simply be left with the quote-unquote input of the log. Okay, and if that doesn't make sense, that's okay. We're going to look at a lot of examples. Log asks the question, what power must I raise a to in order to get x as a result? What that means is you look at your base and you say, well, what must the exponent of this be in order to get that value? So let's look at the first example. I have log base 10 of 100 equals what? All this is saying is take your base, what exponent must my base have in order for it to equal that input value? Well, 10 to the what equals 100. Well, isn't 10 squared equal to 100? Yes. So log base 10 of 100 equals 2 because 10 to the second power equals 100. Okay, let's look at this one. Example 2, log base 2 of 8. How do I rephrase it in a sentence? 2 to the question mark exponent equals 8? So 2 to the what equals 8? Well, we know if you take 2 to the third power, 2 times 2 times 2, I get 8. So log base 2 of 8 equals 3. So let's practice some more. Example 1, log base 3 of 81. What this is saying is, what exponent does 3 need in order for it to equal 81? 3 to the what equals 81? Well, what is that? I know that 3 times 3 is 9 times 3 again, that's 27, times 3 again, that's 81. So I have 1, 2, 3, 4 3's. That tells me 3 to the 4th equals 81. Therefore, log base 3 of 81 equals 4. 3 to the 4th equals 81. Okay, log base 12 of 1. What exponent must 12 have in order for it to equal 1? Well, that question mark has to be 0. Anytime you have an exponent of 0, it equals 1. It is the only way to get something equal to 1 that is an exponential. Okay, 2 to the what exponent equals 32. 2 to the question mark equals 32. So how many? Well, I have 2 times 2 times 2 equals 8 times 2 times 2. So there's 5 2's there. So 2 to the 5th equals 32. Thus, the log base 2 of 32 equals 5. Last one, log of 10. Now, as you notice, there isn't a base there. So what is that base if there's nothing there? Well, we count in numbers by tens, 10, 20, 30, 40, etc. So the natural base of log is going to be the number 10. So if there is no base there, you assume that the number there, the base, is 10. So this question's asking, here's my base of 10. What exponent does it need in order for it to equal 10? Well, 10 to the first power equals 10. So log of 10 equals 1. The natural base of log is 10. Like I said, if there is no base there, you automatically assume it is 10, and this is called the common log. The common log is the most basic log. It's the one with a base of 10. Okay, turn the page, please. Here's some graphs. These are the log functions. If you notice, when I rotate these, those are the exponential functions. It's because log is the inverse of the exponential. So let's look back at this. This is the log graph. In this case, my base of the log function is between 0 and 1. If my base of the log function is between 0 and 1, then the graph will be constantly decreasing. Decreasing as I go left to right. The reason that's the case is because the log function is the same as this exponential. So not a to the x, but a to the y, because it's the inverse of the exponential function. So if I have a to the y equals x, and I know my a value is between 0 and 1, I essentially have something smaller than 1. So let's say, for example, my base is 1/2. If I had 1/2 and I multiply it by itself, 1/2, I get 0.25, which is smaller than 1/2. If I multiply it again by 1/2, I get 0.125, which is even smaller. Then times it by another 1/2, I get something even smaller. Multiplied by another 1/2, I get something even smaller. So as you multiply a number between 0 and 1 by itself over and over and over, that number is going to get smaller and smaller and smaller progressively. That's why if your base of the log is between 0 and 1, you will have a decreasing function. If the base of your log is bigger than 1, naturally it's going to be increasing, because what that's saying is I have a number bigger than 1 and I'm multiplying it by itself over and over and over. Naturally that's going to get bigger and bigger and bigger. Okay, so that's why you have an increasing graph when you have a base of a log that is bigger than 1. So here are some attributes